So we are off to, or still here on chapter 7 last time. And in chapter 7, we talked about really equations and balancing equations. Remember, an equation basically has reactants, which are our starting material, and they go to products. And when we do use an equation, always in pretty much every situation, it does need to be balanced. And when we do balance the equations, remember that when we go to do that, it is only the coefficients or the numbers that come in front that we use to balance out the equation. We can continue to do so until essentially we have the same number of elements on each side of the arrow. The idea behind that obviously is the law of conservation of mass. We don't create nor destroy any elements along the way in a chemical reaction. It's really all about breaking bonds and making bonds, and that's all about electrons. So we don't do anything with the nucleus or protons, and that means that we do have conservation of the elements along the way in the chemical reaction. Remember, a few things that we want to remember is when it's all said and done, it needs to be all whole numbers. And it does need to be the simplest set of whole numbers. Remember that you absolutely, as we talked about, and we did a few examples, you can use a fraction to balance your equation. But remember that you do need to clear the fraction when it's over. And remember that when choosing sort of the fraction, if necessary, the top number is the number that you need to balance the equation at that point, and the bottom number should match the subscript that is there. Also remember that if you do have, for example, some polyatomic ions in the equation that you need to balance, a lot of times it's easier to kind of keep those guys together and then balance them as whole units rather than element by element. You can still go element by element, but there's definitely a lot more sort of multiplying in and multiplying out that you'll have to do. We then talked about sort of types of reactions, and remember that basically there's two big categories of reactions. There's the redox reactions, and then there's really double displacement reactions. And there's really three reasons why a reaction takes place. And as we talked about, it's really making a solid or a precipitate, forming water, or electrons being transferred. And electrons being transferred is essentially the whole purpose of redox reactions. It's all about oxidation and reduction. Remember that if something is oxidized, it loses electrons, becomes more positive as it goes from, say, reactants to products. If something gets reduced, then it gains electrons. Thank you very much. As it goes from reactants to products, and it will become more negative. The double displacement reactions basically take care of all other reactions, are the other two reasons, and that is forming a solid and also forming water. Remember that under these sort of big categories of reactions, you can more specifically classify the same reaction. Under redox, you have synthesis reactions or combination, which is basically two things make one thing. You have decomposition, which is basically the opposite. One thing makes multiple things. You have single replacement reactions. And that is when you have basically one thing by itself and an ionic sort of compound. And this guy will come in, for example, and kick that guy out and make a new ionic compound, and the guy will come out by itself. We also have combustion reactions, which most of the time is organic molecules plus some oxygen, CO2, and water is very common. Are really all you need for basically a combustion definition is oxygen being present, technically speaking. Now, under double displacement reactions, that's where we have precipitation reactions. And that's when some type of solid is made. We also have acid-base reactions or neutralization reactions, and that's basically where water is made. All double displacement reactions are pretty much the same deal. For a double displacement reaction, it is two ionic compounds. That's how you recognize them. Learn my alphabet there. There you go. And always when you have two ionic compounds, the two positive guys will switch partners. And that will give you two new ionic compounds on the other side. And this is really where we form either a precipitate or water. So again, if one of those forms a solid, that again is known as a precipitate. And if maybe one of them forms water, that is again probably a result of that acid-base reaction. As we also saw, you definitely can classify reactions, the same reactions in multiple ways depending on what you're looking at. I think we looked at the magnesium plus the oxygen makes magnesium oxide, which is a synthesis reaction. It's a redox reaction, and it's also a combustion reaction. So you can classify the same reaction in multiple ways. Any questions on any of that stuff there that we talked about? All right, then continuing on here, we're going to do some calculations, some important calculations. We're going to talk about molar mass and Avogadro's number. So let us start with the mole. So the mole, which is not the furry guy, but the mole is a unit in chemistry that represents a certain amount of something. So in life, we have a lot of words that we use that does represent like a certain amount of something. When you tell somebody you have a pair of something, that usually represents that you have two of them. If you have a dozen donuts, you got 12, unless you got the baker's dozen, they got 13, but we'll go with the dozen for 12 there. If you got a gross of pencils, that's oftentimes what that used to be used for. You have 144 sort of pencils. So in chemistry, we do have a sort of word that represents a certain amount of something, and that is the mole. And the abbreviation for the mole is MOL. And I make this point that they had to abbreviate it some way, so they cut off the E. But oftentimes what people really screw up on is when they see MOL, their minds automatically jump to molecules, and that is incorrect in this case. So if you see MOL, it is moles. If they want molecules, they will write out the word molecules in chemistry. So again, MOL is definitely moles, not molecules. And again, that's a very common mistake that people make when they use that. So what is a mole? A mole basically is the amount of substances there are in our carbon-12 isotope, in 12 grams of our carbon-12 isotope. If you remember, the carbon-12 isotope was the isotope they used to figure out the atomic masses on the periodic table. And it really is a conversion factor. We'll get back to those pictures in a second. And it does equal an actual number. And here, 1 mole of anything will equal 6.022 times 10 to the 23. Now, the units associated with this, it does change. So it depends on the situation. These could be atoms. These could be molecules. These could be particles. These could be pizzas. These could be shoes. Well, so 1 mole of anything will equal that number, just like when you say a pair of something equals 2. When you say a mole something, it equals that 6.022 times 10 to the 23. I would say outside the occasional pizza, probably in here in chemistry, these are the two common units there that you will use with Avogadro's number, which are atoms, are molecules. And it doesn't really matter what it is. This is Avogadro's number. And that's 6.022 times 10 to the 23. What that means is if I had 1 mole of hydrogen, I would have 6.022 times 10 to the 23 atoms of hydrogen. If I had 1 mole of carbon, I would have 6.022 times 10 to the 23 atoms of carbon. You could also use it for compounds as well. If I had 1 mole of water, I would have 6.022 times 10 to the 23. And these would be molecules of water. And again, because water is a molecule, not just an element by itself. So we use the units of molecules with Avogadro's number. If I had 1 mole of methane, I would have 6.022 times 10 to the 23 molecules here of methane. So what is Avogadro's number used for? It really is pretty much used as a conversion factor. And it's a conversion factor that allows you to go between these units of moles to atoms or molecules and backwards. So moles to atoms or moles to molecules and backwards is really what you would use Avogadro's number in a calculation. That means that if you have moles and you want atoms or molecules, you're going to take 1 mole of whatever it is will equal 6.022 times 10 to the 23 atoms or molecules. The moles will cancel and you'll be left with atoms or molecules again. Or if you're starting with atoms or molecules, you're going to divide by Avogadro's number, 6.022 times 10 to the 23 atoms per mole. Atoms will cancel, and that will leave you with moles. So once again, it is a conversion factor. You can put Avogadro's number up on top, put Avogadro's number on the bottom. You want to use it like any other conversion factor. Opposites cancel. The other problem that people have with Avogadro's number is they learn this number and feel like they should use it in every calculation they ever do. And you should not use Avogadro's number in every calculation that you do. So when should you use it? You should use it if they give you a number that is in atoms or molecules. You most likely will need to use it to convert to moles. Or if they ask you to solve for something that's in atoms or molecules, then you probably will use it to solve for that. There's no mention of atoms or molecules. You should leave Avogadro's number on the side and not use it. And again, that's a very common mistake people make is they try to incorporate it. Sometimes people get lucky, they incorporate it incorrectly at the beginning and then incorporate it incorrectly at the end, and they cancel each other out and they actually get the right answer. But you don't need to use it in every calculation. Those are the key words you want to look for. Did they give me something in atoms or molecules, or am I looking for something in atoms and molecules? The answer is yes to that. Then somewhere along the way, you're going to need to use Avogadro's number as a conversion factor. Any questions on that there? Now, as I mentioned before, the MOL is the abbreviation for moles. And again, just like when we say we have a dozen oranges, means we have 12 oranges. If you say you have 1 mole of hydrogen, you will have 6.022 times 10 to 23 atoms of hydrogen. You can do that for anybody on the periodic table. It's the same number. And again, anything that's a compound like water or methane or things like that, you could also, again, use Avogadro's number, except that it will not be atoms. It'll be used in the form of molecules because those guys are molecules. Another really important, honestly, conversion factor is molar mass. And molar mass has units of grams per mole. And where we calculate the molar mass is from the periodic table. So we go to the periodic table. We look up hydrogen on the bottom. It says 1.008. So earlier on in an earlier chapter, we saw that that was our atomic mass, an AMU that we saw before. We could also pull that number off the periodic table and use it as the molar mass for that particular element. And much like the name implies, molar mass, mole per mass is how many grams there are per mole. And we typically pull that number off to 4 significant figures. And when we would pull that off for hydrogen, what that would mean is there is basically 1.008 grams of hydrogen and 1 mole, basically, of hydrogen. That means the molar mass is 1.008 grams per mole. The number always stays with the grams and the bottom unit is 1 mole basically. So the mole is always 1. Number always stays with the grams part. You could do that for hydrogen. You could also do that for something like water. If you wanted, say, the molar mass of water, you basically just add up all the parts that are there. So we have hydrogen there. If we also look at the periodic table under oxygen, we will see 16, probably see 15.9999, but we'll call it 16. Once again, what we would do here if we wanted to calculate the molar mass here of water is there are 2 hydrogens. Each hydrogen is 1.008 grams per mole from the periodic table. We would then add it to our other element there, which is oxygen, and that is 16 grams per mole for the oxygen. We would add that up, and that would give us 18.02 grams per mole is the molar mass of water. That again means that for every 18.02 grams of water you have, that represents basically 1 mole of water. You could do that for anybody on the periodic table. I could do it again for any type of compound or molecule and add up all the parts to it. Uh, and numerically speaking, the conversion between AMU per atom, which is how we kind of used it in that first chapter, and grams per mole is numerically, they come out to the exact same number. So when we look at something like sodium, which is 22.99 AMU per atom, it is also 22.99 grams per mole. So numerically, they are the exact same number as we used them before, except the units are different. That is a really important conversion factor. We use it a lot in chemistry, and what we use molar mass as a conversion factor for is we use it to go from grams to moles or moles back to grams. So that is the conversion factor that we use to do that. You can, for example, if we took something like water, you could use it like a conversion factor, 18.02 grams of water over 1 mole of water. Or if you needed it the other way around, I'll put it on the other side since I ran out of room. 1 mole of water could go up on top, represents 18.02 grams of water. So really molar mass for all intents purposes is very similar to Avogadro's number. It pretty much is just a conversion factor. And it's that conversion factor that allows you to go again from grams to moles or moles back to gram. Any questions on that? What is the relationship between, say, molar mass and Avogadro's number? They are all related to each other. For example, 1 mole of hydrogen atoms, as we just talked about, would have 6.022 times 10 to 23 atoms of hydrogen. And 1 mole would also be 1.008 grams of hydrogen. So they are all related to each other that way. That all represents a mole. Same thing if we had 1 mole of water, that would represent 6.022 times 10 to the 23 molecules of water. And as we just added up on the periodic table, that would represent 18.02 grams of water. So if you need to go all the way from, for example, atoms or molecules to grams, you need to use Avogadro's number and molar mass to do that. Or if you're starting with grams and need to end up at like atoms or molecules, you need to use the molar mass and then Avogadro's number to get there. And that's what you can see here. Again, 1 mole of silver has a mass of 107.9. Any questions on that? That is also why on that picture I kind of skipped over. Let's come back, take a look at it here, I think. These all represent 1 mole samples of each of these things. That's sulfur, that's iron, and so forth, sodium chloride. Why does 1 mole of all these things look different? That is because 1 mole of these things represent a different amount, right? If I'm talking about sulfur, if I look on the periodic table, 1 mole of sulfur represents 3207 grams, right? If I look at iron on the periodic table, not just F, but Fe would be good. 1 mole of that represents 5585 grams, right? So although they all represent 1 mole of everything, it does represent a different amount in terms of grams. And if I did 1 mole of sodium chloride, sodium is 2299, chlorine is 3545. And if I did that, that would be for its molar mass 2299 grams per mole for the sodium, plus 3545 grams per mole for the chlorine. So that's for the sodium, that's from the chlorine. Again, those numbers are coming from the periodic table. And if we look at this 22.99 plus 35.45, that will give us 58.44 grams per mole. That would be the molar mass for something like sodium chloride. Again, we're just adding up all the parts. Any questions on that there? I will say that sometimes when you do calculate the molar mass of an ionic compound, some people will refer to it as the formula mass because it's ionic and stuff like that. For our purposes here, we'll just call everything molar mass when we calculate it. But if you see formula mass or formula unit, sometimes for ionic compounds, they use those kind of terminology for it. Any questions on that there? All right. So once again, as I mentioned, we could use these guys as conversion factors. And again, I would say probably out of the two in chemistry, outside of this chapter, probably outside of this chapter and other parts of chemistry, out of the two, probably molar mass is going to be used a lot more than using Avogadro's number. Again, we oftentimes, in a lot of calculations that we do in chemistry, we need things in moles, or we want to figure out how many grams we produce. So again, that molar mass conversion is used a lot. All right, so why don't you give these guys a go and see what you come up with. We want to know how many moles of helium are there in 5.46 grams of helium, and then how many grams of zinc are there. So in case you don't have a periodic table, if you find helium on the periodic table, you will see 4.003. And if you see zinc on the periodic table, so it depends which one you look at, you might see 6538 or 39. This is 38, I think. Yeah. Okay, so let's take a look. So we want to know how many moles of helium are there in 5.46 grams of helium. So the first question is, do I need to use Avogadro's number here? The answer is no. So there's no mention of atoms. There's no mention of molecules. So this is just a grams to mole conversion. As they gave us grams, we're looking for moles. Remember, it is the molar mass. That's your conversion factor. To do that, you would go to the periodic table and grab that number that's underneath helium here. And again, that would mean that there are 4.003 grams of helium and 1 mole of helium. That again will give you two conversion factors that you basically can use. And that's really what you want to think about it when you're doing this. Is just treat them like conversion problems. Keep it simple. Look at we did before where opposites cancel. So, you know, you don't have to worry too much about it. Here they gave us 5.46 grams of helium. And again, just thinking it like a regular conversion type problem, grams of helium up are on top, which means I need opposite for it to cancel. So I need to use conversion factor there on the right, which basically means I'm going to be dividing by the molar mass here. The grams of helium on top and bottom will cancel. And basically we're taking 5.46. We're dividing it by 4.003. And that's going to get us there at 1.36 moles of helium. 3 sig figs based off of really the original number there is what we were looking at. Any questions on that calculation? Again, we're going to take kind of the same approach here for the second problem, which is how many grams of zinc are there in 0.256? Again, the MOL here is moles, so that is 0.256 moles of zinc. Do I need Avogadro's number in this one? Again, I do not need to. In this case, we're actually just doing the opposite calculation, moles to grams. So once again, that is going to be our molar mass. That's going to allow us to pick it off the periodic table to find our molar mass. And that basically means it's 6538 grams per mole for zinc. And that gives us basically two conversion factors, 6538 grams of zinc over a mole of zinc. Or again, you can flip it around the other way, a mole of zinc over 65.38 grams of zinc. Here we're going to start with what they gave us, which is 0.256 moles of zinc. Here, zinc is basically up on top, moles of zinc. So we do want moles of zinc on the bottom. So we do want to use this conversion factor of the molar mass so that opposites cancel. Gives us 6538 grams of zinc per mole. The moles of zinc will cancel. We're going to multiply 0.256 times 6538. Going to give us 16.7 grams of zinc. Question on either of those calculations there. I would say those two are pretty popular type calculations in chemistry. You do that a lot, going from grams to moles or moles back to grams, using the molar mass from the periodic table used a lot in calculations. Any question on those two? All right, want to try another one here. Let's go with, what is the mass in grams if you had one single gold atom? And gold on the periodic table there, 197. All right, so let's take a look and see, do I need to use Avogadro's number in this problem? I do. The key word there is atoms, right? They gave us atoms, so we do need to use Avogadro's number. We are starting with atoms, and we do need to end up at grams. Really, the thing that ties both of those things together are moles. So that is sort of the pathway to get there. That's sort of the guy in the middle of those two units. Here, but don't lose the problem. We gotta go from atoms to moles by using Avogadro's number. Once we have it in moles, we then could use the molar mass from the periodic table to basically go the rest of the way. So in this case, remember that I would say they never give you Avogadro's number. It is just like a number that they expect you to know that you have sort of available to you. And again, that is 1 mole of anything will equal 6.022 times 10 to the 23. And we are going to use atoms in this case because we are obviously have units of atoms. And obviously our molar mass here for gold, coming from the periodic table, 1 mole of gold will equal 197.0 grams of gold. And obviously, this is gold atoms as well. So we're going to start with the 1 gold atom. And again, just treat it like a conversion problem. So I guess I should write 1 gold atom. There you go. Put that unit in there would be good. And again, that unit is on top. So we do need to put atoms on the bottom. So 6.022 times 10 to the 23 atoms per mole of gold. If I stop right at this point in terms of my calculation, atoms of gold will cancel out. I will be left with what unit? I'll be left with moles, right? And again, setting it up in this way with dimensional analysis, if I wanted to just continue on with my calculation, I could clearly see the moles are on top or bottom here. Top, which means I do want to get rid of moles, which means to get rid of them, I need to put them on the bottom, right? So again, you want to continue to make sure you set it up like this with dimensional analysis, because if you wanted to, you could roll with the calculation and use the molar mass now from the periodic table as your conversion factor. Again, 1 mole of gold on the bottom, 197.0 grams on top. The moles will cancel. Just like any conversion we've done before, we're going to multiply whatever's on the top and obviously come back here and divide by what's on the bottom. We're going to make sure that we are using our exponent button for sure. Really on top, we really only have 197 since everything else is a 1. We're going to divide it by 6.022 to the 23. And that will get us something like 3.271 times 10 to the minus 22 grams of gold in this particular case. Any questions on that calculation? If you wanted to, you could have got an answer after the first step there where we used Avogadro's number and then just use that number to do the second part of the calculation. Perfectly fine. Again, I would probably not round too much after that first calculation if you did get an answer and continue on with it. The reason I went with 4 significant figures is really one gold atom would be like one thing you would count. So it's kind of like an exact number. So I went based off of the molar mass here to 4 significant figures is why I went there. Any question on that one there? I'll try a couple more here. Let's see, how many moles and molecules are in 9.73 times 10 to the minus 22 grams of water? Also, if I had 3.25 times 10 to the 12 molecules of C2H4, how many moles and grams would that be? All right, so see what you come up with. We give you some numbers in case you don't have periodic table. Hydrogen 1.008, oxygen 16, and carbon, I think will work, 12.01. All right, so take a few moments looking for 2 answers for each of those. See what you come up with here. Okay, so let's take a look, see how you're doing. Again, here on the first one, we see the keyword of molecules is what we're looking for. So that definitely should tell us we're also looking for moles. This definitely tells us we are using Avogadro's number somewhere along the way. And since we also want moles and we're given grams, so remember grams to moles, and the moles are the thing that kind of ties all those units together to molecules. And again, it's the molar mass first off that will get us to moles, and then it's Avogadro's number on the back end there to get us to molecules. Remember, again, you have Avogadro's number, which is that 6.022 times 10 to the 23 number. So we're going to start here with 9.73 times 10 to the minus 22 grams of water. Before we could do that, we do need the molar mass here, right? Which is our first conversion here for water. So we would go to the periodic table and basically just add up all the parts that are in water like we did earlier. So again, there are 2 hydrogens, each from the periodic table is 1.008. We're going to add it to our 1 oxygen, which from the periodic table is 16 grams per mole. That gives us a molar mass for water of 18.02 grams per mole. Again, the grams gets the number and the moles are always 1, basically. So that's the first guy that we're going to use for our conversion factor here. And we got grams up on top. So we do want grams on the bottom. So we're going to put our 18.02 grams on the bottom that we got from the periodic table. And that's going to be our moles of water. The grams here will cancel. I am going to get an answer here since that is one of the questions that was asked, which is how many moles. So I am going to get an answer. 9.73 exponent button negative button 22 divided by 18.02. And that gives us 5. We'll call it 40 times 10 to the minus 23. The units here are moles of water. And again, I got the number because that was one of the things that we were looking for. First off, any questions on that calculation? Now we're actually right here in terms of our progress. we do need to get to molecules. So again, it is Avogadro's number that's going to allow us to do that. So we're going to take our 5.40 times 10 to the minus 23 moles of water. Once again, remember, we're going to use Avogadro's number, which is 6.022 times 10 to the 23 molecules per 1 mole. So here we want moles to cancel. So moles are going to go on the bottom, and Avogadro's number here is going to go up on top, so that we do end with molecules and not moles. So we do end with molecules. The moles will cancel, and that will get us here. 32.5 molecules of water in this case. Any questions on either of those calculations? Yeah. It is, yeah. Yeah.
And plus the 16.
Yeah, so you go 2 times 1.008 plus 16 gets you 18.016, like on your calculator. So typically when you do calculate the molar mass, like we were talking about before, you go to 4 significant figures. So that's why typically it should round to 18.02 in that case, yeah. Now, unless you use like the periodic tables, they like to put in some books now that is like 1.01, so you get a slightly different number, but it should really be 1.008 for hydrogen. Other questions? Okay. So we'll do kind of the same thing here on the bottom. We do need to use Avogadro's number. We're actually just going backwards in this calculation. We're starting with molecules. Then we're going to moles, and then we're going to grams. So here we do need to actually open up with Avogadro's number. That will get us the moles. And then we need the molar mass from the periodic table to take us the rest of the way. So while we're at it here, why don't we just calculate the molar mass of this guy, because we will need to use it. So once again, to get the molar mass, all we're doing is just adding up all the parts here. So for this guy here, we have 2 carbons from the periodic table at 12.01 grams per mole. We then will add it. There's 4 hydrogens, so 4 times our 1.008 grams per mole from the periodic table. And that will give us a molar mass of this guy of, we'll call it 2805, looks like. So 28.05, again, grams per 1 mole would be the molar mass of this particular compound. And again, we're going to need to use that here. Actually, on the back end, we're going to need to use that. But here we'll start with the front part of the calculation. So we have 3.25 times 10 to the 12 molecules of C2H4. We'll use our Avogadro's relationship just like above. Here we're going to go opposites. So it is going to be Avogadro's number on the bottom here, because that has the units of molecules per mole of C2H4. Molecules will cancel. Again, I'm going to get a number here since that's part of the question to figure out how many moles. So we do actually need the numbers. So otherwise, we could just continue on with the calculation if we didn't need the number. Make sure, again, you use your exponent buttons when you punch both of these numbers in. And you'll get something like 5.40 times 10 to the minus 12. And these would be moles of C2H4. Any question on that calculation there? Now, since I do need to continue on, that's where my molar mass is going to come into play. That's going to allow me now to go from moles to grams. So we'll continue on with that number, and I'm going to actually continue on with the whole number of my calculator. So once again here, setting up dimensional analysis, we actually see moles are on top in this case. That means we do need moles on the bottom, and our 28.05 that we got from the periodic table should go up on top so that they cancel. And we're going to multiply that guy by 2805. That's going to give us 1.51 times 10 to the minus 10 grams of C2H4 in this case. Any questions on any of those steps? So again, you got to remember, you always have Avogadro's number. Most problems will not mention anything about Avogadro's number. Again, it's just something that they assume that you know and know how to use it. And again, molar mass from the periodic table. Really, these are just conversion factors. Treat them like conversion factors. Set them up like conversion factor problems, so units oppositely cancel. Then you don't have to worry about should I divide or should I multiply. Just go opposites in the units, and that will take care of the should I multiply or divide type thing for you. Any questions on grams, moles, Avogadro's number? Before we move away from this topic, let's talk about one other thing that does sometimes occur. So, why not? Let's steal the one we got on the bottom there. So let's say we had our C2H4 there, and 2805 was the molar mass, I believe, 28.05 grams per mole. And let's say we had let's say we had here the, actually we'll just use whatever number we just got there. We had molecules, 3.25. So we'll use the 3.25 times 10 to the 12 molecules of C2H4. Now, what I want to know in this case is how many grams of carbon is that? So in this particular problem, we're not actually interested in the entire thing of C2H4. We're actually just interested in the carbon part of it. So how can we get to kind of the whole thing to just the carbon part of it? We actually can use the formula itself as a conversion factor. So when you look at these numbers on the bottom, they do represent the moles of each of those guys. So we could actually come up with some conversion factors from the actual formula. And we could say, for example, in 1 mole of the entire thing, how many moles of carbon would there be? There would be 2 moles of just carbon. And again, we could use that as a conversion factor to go from the whole thing to just that carbon, which we're interested. And we could also say in 1 mole of the entire thing, there would be how many moles of hydrogen? It would be 4 moles of just hydrogen. So in order to use these conversion factors are all moles, which means before we could use them, we do have to convert our number here into moles so that we could use them. So if we have molecules and want moles, we need to use Avogadro's number to do that, right? So that's what it takes us from molecules to moles. So if I take my 3.25 times 10 to the 12 molecules of C2H4, and I use my Avogadro's number like I used previously there, 6.022 times 10 to the 23 molecules on the bottom per mole of C2H4. And if we get an answer at this point, we might have had that answer on the previous question here, 6.022 to 23. We end up with our 5.40 times 10 to the minus 12 moles of C2H4. Now that I have the moles of the entire thing, this is where I could use my formula as a conversion factor. So again, I'm just going to use it like a conversion factor, and I want to go from the whole thing to just carbon, which would be here. And again, we want to go opposite. So I have moles of the whole thing on top, which means moles of the whole thing needs to go on the bottom, right? And 2 moles of just carbon needs to go on top. Moles of the whole thing cancel. And if I got an answer at this point, 1.08 times 10 to the minus 11 moles of carbon. Any question on that there? Is that my answer? That's moles of carbon, but I actually want grams of carbon, right? So what do I need to go from moles to grams? I need the molar mass of carbon. And that again is our 12.01 that we get from the periodic table. So to finish this out, 1.08 times 10 to the minus 11 moles of carbon. I could use the molar mass from the periodic table, 12.01 grams of carbon per mole. And that will get me here that there are about 1.30 times 10 to the minus 10 grams of carbon in that particular compound. So sometimes you might be asked about not the whole thing, but maybe one element in a compound, and you could actually use the formula as a conversion factor. Any questions so far on what we've been talking about? Why don't you try one of those here? Let's say we had 45.5 grams of CO2. How many moles of oxygen and grams of oxygen would that have? All right, so why don't you give it a go and see? Again, carbon 12.01 and oxygen 16 still of CO2. And we want to know how many moles of oxygen there are and really grams of oxygen. So in this formula, we're not interested really in the whole entire formula, the carbon and the oxygen. We're interested in really just the oxygen part. So this is where we can use the formula to really figure out how much of just oxygen it is. And it's going to be a mole to mole sort of relationship. For 1 mole of CO2, we can see from the formula that there are that number on the bottom, 2 moles of oxygen, which is really what we need to use in this particular problem. You could also do it for carbon if you're interested in just the carbon, but in this case, we're just interested in oxygen. So you can just really focus on the oxygen. What understanding that conversion tells you is in order to use it, right, I need to get everybody into moles, right? It's the only way to use that because everybody else here is in moles, and this is going to give us basically a conversion factor that's moles and moles. I need to get this guy into moles so that it will cancel out with the moles of this guy. So that is really now a grams to moles conversion that I do need the molar mass. And this is what I was saying about earlier, that here you do need the carbon so that you can get the correct molar mass for CO2. So if we look up on the periodic table for CO2 and get all the parts, we need 12.01 for our carbon that's there. There are 2 oxygens, each at 16. Gives us 44.01 grams per mole as the molar mass of CO2, the entire thing. And we need that really as a conversion factor to turn our grams of CO2 into moles of CO2. So we can use this conversion factor to get it to just oxygen by itself. So that's the part where we do need the carbon definitely involved to do this part of the conversion. So let's start with that 45.5 grams of CO2. Again, we're going to use this as a conversion factor. So opposites tell us that grams need to go on the bottom and moles of CO2 need to go up on top. If I stop my conversion right at this point, the units I am in are what? Moles of CO2. And that's still moles of the entire thing. And that's really not what I want, but it is good because now it's in the proper units, that CO2, that I could use this conversion factor. And that's what I'm going to do. So if you want to get an answer, you can, or if you want to just continue on with the calculation, you can. It's up to you. The moles of CO2 up on top. So now I know I need to put the moles of CO2 on the bottom. And now this is the move that's going to get me to just oxygen by itself. 2 moles of just the oxygen. Here, the moles of CO2 will cancel. At this point, if I stop my calculation, I'm in moles of CO2, right? Sorry, I'm in moles of O by itself. And that actually is an answer I'm looking for, right? One of the answers I'm looking for is how many moles of oxygen there are. So I'm actually going to calculate it here. That's going to be 45 point, my calculator works, 45.5 times 2. Again, multiplying everything on top, dividing by what's on the bottom, which is 4401. And again, multiplying and then dividing. And that's going to give me one of the answers I'm looking for, 2.07 moles of oxygen. Question on that part of the conversion. Now that I have it in moles of oxygen, it is now a conversion between moles to grams, which is just the molar mass from the periodic table. In this case, though, I need the molar mass of what? Just oxygen, right? Because that's what we converted to. So that is our 16 grams per mole that we got from the periodic table. So here we'll take our number, 2.07 moles of oxygen, using the molar mass from the periodic table, 16 grams on top. And we need moles of oxygen on the bottom so that they cancel. And that will yield us here approximately 33.1 grams of oxygen in this case. You could also do, like I said before, a similar calculation for carbon by using the relationship from carbon in the equation. So to answer the earlier question, in terms of the carbon, you can't eliminate it completely. You do need it here for the molar mass part of the calculation so that you could get really the whole thing into the correct unit, so you can use that kind of mole to mole relationship. Yeah. Any questions on any of that there? Yeah. In this particular case, based on the question, it could have just asked, for example, how many moles of oxygen that is. It could have just asked for how many grams of oxygen, for example, but this particular one had 2 questions. It could have also asked, for example, how many atoms of oxygen there would be. So if I wanted atoms of oxygen, what would I need to use? Avogadro's number, right? I would have to do up to this point, right? Let me get the writing part. Up to this point, and then I can use Avogadro's number if I wanted atoms. So that's also sometimes what you're asked is like how many atoms of oxygen or carbon there would be in that particular one as well. Any questions on that there? All right, so now that we're professionals at this, we're going to put together everything we've been talking about in this chapter, balancing equations and these kind of grams to moles calculations. And we're going to do actually calculations from the actual equation itself. And this is what is known as stoichiometry. And it does basically put together the 2 things we've talked about in this chapter, the equations that are balanced and also those sort of calculations. Stoichiometry revolves around an equation that's balanced. And whenever you do this, that should always be, as we'll talk about, the first thing that you should do is make sure the equation is balanced. Regardless, got to have a balanced equation. When you look at the coefficients in a balanced equation such as this, there are a couple of ways that you can look at those numbers that come in front in a balanced equation. For example, here we could say that there are 2 molecules of H2 react with 1 molecule of O2 to make 2 molecules of H2O. We could use what is referred to commonly as the mole-to-mole relationship, which is actually the relationship we will use in these type of calculations. So you could take those coefficients and say there are 2 moles of H2 react with 1 mole of O2 and 2 moles of H2O. Sometimes people get freaked out about where those numbers come from. It is only basically the coefficient in the balanced equation. So there's no magic of it. It's whatever that number is in the balanced equation that's sitting in front of that guy, that's how many moles there are of it. So that's why, again, it's always important to start with a balanced equation. The last one is not too much used by us, but this is conservation of mass. This is why we balance equations, because if we started with like 4 carbons, we'll end with 4 carbons and they weigh the same on each side. So we'll have the same amount of grams of reactants and products. So let's take a look at this idea of stoichiometry. And stoichiometry uses this sort of mole-to-mole relationship to help you answer questions which are commonly asked, which is, for example, maybe they tell you how much of a reactant you start with, and you want to know if everything went great, How much product should you make? How much product should you get out of that reaction? You could also figure out, if you know how much product you got produced in a reaction, you could do some back calculations and figure out how much reactants that you started with in that particular reaction. The units of stoichiometry that we will use can be really anything. It could be grams, it could be moles, liters for gases, which we don't get too much into here. But very commonly, you are given things in grams. And one of the things you have to do is convert it to moles. So as we've been doing in our previous examples, that's going to be the periodic table, and you're going to need the molar mass to do that. By the way, on the back end of these calculations, you'll have things in moles that will oftentimes be needed converted to grams, which would also be the molar mass as well. So that kind of grams to moles, moles to grams calculations that we just were doing, very common calculations done in these type of problems. And we use, again, that mole method, which is basically simply just the balance coefficients represent the moles of whatever it's in front of in the equation. So there are some steps to follow. You want to write all of the formulas correctly for the reactants and products. This would be a situation if you were given everything in words. You want to, as we talked about with equations, make sure that you have all the proper formulas there. And probably the most important thing in stoichiometry is balancing the equation. If you are not starting with a balanced equation, you're just definitely going to get the wrong answer, because you will not have the right mole to mole relationship, because your coefficients will be incorrect, which will throw off your entire calculation. Then you want to take whatever they give you. And in a lot of cases, they will give you something, and whatever units they are in, you need to get them to moles. And usually that is at some point, a grams to moles conversion that you need to do. Once you have it in moles, you actually could do the stoichiometry part of the problem, which is you want to go to the balanced equation. You want to find the two things you're interested in. One thing you're interested in is whatever they gave you. The other thing is what you're trying to find. So those are the two things you're interested in. And you want to use the mole to mole relationship. That is really what stoichiometry is. It is nothing more than a conversion factor. And sometimes, again, people get freaked out about the whole stoichiometry and the mole to mole relationship, but it is actually just a conversion factor. And that's because they give you information about somebody in the equation that you're not interested in, but you're interested in somebody else in the equation. And there's no table you could go look up of what's the relationship between those. So where you get that conversion factor is from the balanced equation. And that's basically what stoichiometry is. Once you do that, a lot of times you should always be in moles at this point, and you want to convert to some other unit, and that may be grams as well. A lot of times, basic stoichiometry problems can boil down to 4 steps. You want to make sure you got a balanced equation. You want to convert to moles. You want to do the mole to mole relationship. And you want to convert, if necessary, those moles to some other unit. Pretty much these are the 4 steps that you should always follow, in that order, by the way, and you will get to the right answer. You should get to the right answer. I guess the way to say that. If something is done for you, by the way, you just go on to the next step. Don't go backwards. So sometimes people go backwards for some reason. So you just want to keep going forward. So let's take a look and see what we're really talking about here. So let's take a look at this equation. Now, from this one equation, we could actually come up with a bunch of stoichiometry or stoichiometric relationships. So here's all the relationships that we could get, which are really just conversion factors. Instead of looking up in a table, this is where we're going to get our conversion factors from. We could say that for every 2 moles, and that's just the coefficient of CO, how many moles of O2 are there? The number in front is 1 mole of O2. For every 2 moles of CO I put in there, how many moles of CO2 do I get out? You get 2 moles of CO2. For every 1 mole of O2 I put in there, again, with nothing written there, it's assumed to be a 1, right? I get out 2 moles of CO2. These are the three equalities that you could get from this equation. They are equal to each other, not in the sense of 2 equals 1, which clearly it doesn't. They are equal to each other in the sense of if you want this reaction to go, that is the relationship or proportion of those things you got to throw in there to make this reaction go. Now, because these are the three equalities that we could get from this particular equation, just like in regular conversions, for every equality that we have, we could write how many conversion factors? 2. So for the first one, we could say that there are 2 moles of CO over 1 mole of O2, or flip it around. 1 mole of O2 over 2 moles of CO. For the second one, we could say for 2 moles of CO, we get 2 moles of CO2. Or again, we could flip it around. For 2 moles of CO2, we get 2 moles of CO. Lastly, we could say for 1 mole of O2, there are 2 moles of CO2. Or for 2 moles of CO2, there are 1 mole of O2. These are our 6 conversion factors that we could get from this equation. First off, any questions on how I got them? Will I use all of those? The answer is no. You're just going to probably use one, whichever one that you need to use. But those are all the ones that are available to you to use in this particular equation. And once again, you probably only should use one in the problem. Otherwise, something's not probably right to what you're doing. So how would we use this? So for example, let's say that we started with, actually, no, let's say we produced. Let's go with 36.5 grams of our friend's CO2. And we want to know how many grams of O2 did we start with. So we're going to say in this equation, we produced this much CO2. We want to actually know how many grams of oxygen did we start with to produce that much. So we want to follow our 4 steps. So our first step always in a stoichiometry problem is balance the equation. Is the equation balanced here? I'm going to say yes. This equation is balanced off the bat, so that one is good to go. Check. Number 2 is we want to convert whatever they gave us to moles. Do I need to do that in this case? I do, because we were given 36.5 grams of CO2. So I need to take the grams of CO2 into moles, right? And we got to take grams to moles of CO2, and that is the molar mass that we need to use to do that. I think we actually just did that on the previous problem. So I'm just going to steal the number. And again, you would go to the periodic table, and that is where we got that 4401 grams per mole for CO2 from the periodic table. 1 carbon at 12.01 plus 2 oxygens at 16 each. So I think that's the one we just did in the previous problem. So that's really the second step that we want to do, right? So we're going to take the number that they gave us. We're going to do a regular old conversion like we just did, which is I want to take my grams to moles. So I want to put grams on the bottom, 4401 grams per mole of CO2. And I'm going to get an answer in this case. And 36.5 divided by 4401 gives me 0.829. I'm going to take it to a few digits, 36 moles of CO2. First off, any questions on that? And again, that is pretty much from the periodic table of carbon 12.01 and oxygen 16 like we did in that previous problem. We are now at the third step, which is the mole to mole relationship. This is the big stoichiometry part. This is the part that everybody freaks out, which is the stoichiometry mole to mole relationship. So as I mentioned before, we're going to go to our balanced equation and we're going to find the two things that we are interested in. Obviously, one thing we're interested in is the CO2 because that was given to us, right? The other thing is what we're looking to find. What are we trying to find in this case? The amount of oxygen. Those are the two that we're interested in. Now, we already did that relationship, right? And we saw from the equation that for every 1 mole of O2, you produce 2 moles of CO2. Again, that comes from just the coefficients in the equation. That gave us an option of 2 conversion factors. Gave us an option of this conversion factor, and it gave us an option of this conversion factor, right? So now we're not going to overcomplicate it. We're just going to think about it like a regular conversion, which means at this point I have this number. And I want to get rid of CO2. So where should the CO2 go? Yeah, so I should use the conversion factor on the left or right in this case. I should use the one on the left, right? And that's going to get me what I want because I am not interested in CO2 in this problem. I am actually interested in O2. Right there is the big stoichiometry move. It is just from the equation, the coefficients of the two things you're interested in, and you're just going to use it as a conversion factor. So again, this is obviously from the periodic table. This is from the balanced equation. That's going to get rid of the CO2, which we're not interested in, and leave us with O2, which if we do that, we're going to divide it by 2 basically. And that will give us 0.4167. I'm going to take it again to a few digits, bless you. And that gives me moles of O2. Any questions on that part of the calculation? I am not at this point until the very end. So really, none of the answers that I put on there so far are really an answer that we're looking for in this question is really the answer. So just like this, I'm kind of doing it in parts, and you could do this all in one calculation if you want, but I'm doing it in parts, so I'm not going to round too much till the end, and then at the end, we'll clean it up to the proper number of significant figures. Yeah. Other questions? All right. Now, if I was interested in how many moles of O2, right, I could just put a box on it, I'm done, right, at this point. But in this case, I'm not interested in moles of O2. I'm interested in grams. So I do have to do the 4th step. Sometimes you might not need to do the 4th step if you're interested in moles. And by the way, when you get to the 4th step, after the 3rd step, you should always be in moles. So if you're in some other unit other than moles, you did something wrong. So you should always be in moles at this point. So I'm going to do the 4th step, which is take those moles to some other unit, which in this case is grams. So I now need to go from moles back to grams in my 4th step. And how do I go from moles to grams? I need what? I need the molar mass from the periodic table. By the way, I need the molar mass of what at this point? Of oxygen, right? We're done with CO2. So we again need to go back to the periodic table and get the molar mass of O2, which in this case is basically 2 times 16 or 32 grams per mole. 32 grams per mole of oxygen. And here we're going to again put the 32 up on top so that we do end up with grams. We want the moles on the bottom. And again, that comes from the periodic table. And that will give us our final answer here, which is times it by 32. At this point, to answer your question, I am going to round it to 13.7 grams of O2. And that is really based off of the only number that was in the problem, which was 3 significant figures at this point. It is, trust me when I tell you these type of problems are just those 4 steps. Just go in order, do each of the steps if necessary. If something is done for you, skip the step, go to the next step. It's always those, no matter how crazy it may look, no matter how big the numbers are, crazy the formulas, it's just those 4 steps in a row. What does that number really means? It means that if I wanted to produce, for example, 36.5 grams of CO2 in this reaction and everything went perfect, I would need to put in there 13.7 grams of oxygen to produce that much of the CO2 in this reaction. Any questions on any of those steps there? Yeah. For the final answer really is, you could look at the molar masses. There are 4 significant figures, but this guy's 3. So it is the least, since we're still really doing only dimensional analysis, which is multiplying and dividing. And that is always going to be basically sig figs, and that would be the least. You could usually, in most cases, ignore the molar mass and a lot of times just go to the first number. Now, you're welcome. A very common mistake that people make is this. Remember that when you are asked to calculate the molar mass, for example, we got an equation like this, right? Now, when you're asked to calculate the molar mass of CO2 like we did, it is based off of only the formula. So again, 2 times 16 for our oxygen, plus our 12.01 for our carbon, gives us our 4401 grams per mole. And what I mean by that is what the molar mass means, is grams per 1 mole of that. Very common, people screw stoichiometry calculations up because they go, oh, there's a 2 there. Let me include that with my molar mass calculation. And you should not do that. So in these calculations, or whenever you need to calculate the molar mass of whatever you're calculating, it should be based on just the formula by itself, one of the formulas only. Because we take into account that too when we do the stoichiometry in these calculations. So if you take it into account with your molar mass and in stoichiometry, you're going to get the wrong answers. So molar mass, whenever you calculate, should be based just on the formula. Just like if I was going to do the CO here, this is how I would calculate the molar mass of the CO. I don't really care that it has a 2 here, because again, it has no effect on the molar mass, should just be the formula by itself. So sometimes people try to kind of combo those together, like the coefficient and the molar mass, and you shouldn't do that. You might get lucky, but most of the time you'll probably get it wrong because you did it that way. So molar mass always based off just the formula, one formula by itself, add up all the parts. Any questions on that there? All right, so let's take a look at some here. Maybe this is pretty much what we just talked about, so I'm just going to kind of scroll through it here, I think. And why don't you try this one here? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. We want to know how many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water. So lithium metal is Li, yeah. Water is H2O. Hydrogen gas is H2. Remember, hydrogen is a diatomic molecule. And lithium hydroxide, LiOH. So this is the unbalanced equation. So we'll give you a helping hand with that one here. To form means arrow, hydrogen gas, and lithium hydroxide. All right, so balance it up. Follow these steps. You want to balance the equation. You want to convert to moles if needed. You want to do the mole to mole relationship. And you want to convert those moles to some other unit. All right, so see what you come up with. So let's take a look. So first off, obviously, this would be an example if you're given everything in words. As I did here, I didn't really care about the balancing part. Again, I wanted to make sure I got all the proper formulas down first, and that is the proper order to do it, and then you should balance it. So clearly it is not balanced, so we do need to start with that, and hopefully you got it balanced. I feel like a 2 there, maybe a 2 there. I feel like I'm just throwing 2s up on the board, but hopefully all those 2s will work. I think we should now be balanced. We got 2 lithiums on each side. We got 4 hydrogens on the left and 4 on the right, and 2 oxygens on each side. So we are now balanced, right? Now, the only thing given to us is we're going to react 5.32 moles of lithium, and we want to know how much hydrogen we're going to get. And this is really the purpose of stoichiometry. It is they give you some information about somebody in the equation, but you're really interested in somebody else. So step number 2, which is convert what they gave us into moles. Do I need to do that? I don't. It's already done for you. So don't unconvert it and reconvert it. It's already done. So it's in the proper units that we need. That means that we can now go to step number 3, which is the big stoichiometry part. So we want to find the 2 things we're interested in the equation. And one thing is whatever they gave us, which in this case is lithium. The other thing that we're interested in is what we're trying to find, which in this case is the hydrogen. And this is where we're going to get our relationship, which is for every 2 moles of lithium, and again, that is just the coefficient, we get out how many moles of hydrogen? 1 mole of hydrogen. That is really the mole to mole relationship that's going to allow us to do this problem. It's really the conversion factor, which if we wanted to write the conversion factors, we could. It would look something like this, or it would look something like this. And now we can actually do the calculation. So we're going to take our 5.32 moles of lithium. We're not interested in lithium, so we do want lithium in the opposite location, which means it does need to go on the bottom. So we want to use conversion factor there on the right. 1 mole of hydrogen gives us 2 moles of lithium. The moles of lithium cancel. And again, that is the big stoichiometry move there. And that's going to be 5.32 basically divided by 2. Gives us 2.66 moles of hydrogen. That is step number 3. Step number 4 is to take the moles and convert it into some other unit. Do I need to do that in this problem? I actually don't, because they're looking for moles of H2, which means I put a box on it and I'm done with this problem, right? And again, if I did want grams of H2, what would I need? I need the molar mass of H2 from the periodic table. So if I wanted to know how many grams that would be, I would have to go to the periodic table and get the molar mass of H2 in this case. And that would be like step number 4 if you needed to. Any questions on any of those steps there? All right, so let's try one more here. Same equation, same deal. Let's just start with, though, we're going to start with, not that, we're going to start with maybe this one here. There it is. How many grams of H2 would you form in the same reaction if you started with 81.75 grams of lithium? Let me give you some numbers. Lithium is 6.941. Oxygen is 16. And hydrogen there is 1.008. Again, follow the same 4 steps. Balance the equation. Convert to moles. Mole to mole relationship. And moles to some other unit. Okay, so let's take a look at it since we're getting to the end here and see how you're doing. Again, trust me when I tell you, just follow these steps. So balancing the equation, we are good from the previous problem we did. So we will then move on to step number 2. The only thing that was given to us in this case is 81.75 grams of lithium. We are interested in how many grams of hydrogen that would be. Do I need to do step number 2, which is convert to moles? I do, because this is in grams. It needs to go to moles, and that's going to require the molar mass of lithium in this case. So step number 2, we're going to use the molar mass of lithium, which is 6.941 grams per mole of lithium. And we'll take the number that they gave us, 81.75 grams of lithium. Again, doing a molar mass conversion, so we want the grams on the bottom so that they cancel. It's going to leave us with moles of lithium up on top. And if we get a number at this point, we were at 81.75 divided by 6.941 will give us an 11.7778. Again, I'm taking it to a few digits because this is not my final answer. That is step number 2, again, from the periodic table where we get that from, yeah? Any questions? So step number 2 is done. Now is really the stoichiometry part, right? So this is the big mole to mole relationship. So once again, we're going to go to the equation and look at the 2 things we're interested in. One is lithium, which was given to us in this problem. And again, we're looking for hydrogen. So that's going to give us the same relationship of 2 moles of lithium gives us 1 mole of H2. And again, that will give you your same 2 conversion factors that you could use like we did last time. So taking the answer that we got from the previous step and continuing on, we want to get rid of lithium, remember? So we're going to put lithium on the bottom. So again, we're going to use this conversion factor. That's what's going to allow us to get the hydrogen gas up on top. And our moles of lithium here will cancel. So we're again going to divide this basically by 2. And that will get us something like 5.8889 moles of hydrogen. Any questions on that? And that is the big stoichiometry move in step number 3. In this case, do I need to do step number 4, which is take those moles to some other unit? I do, because we're looking for grams, right? So we do need the molar mass here, but at this point we do need to remember that we have now converted to H2, which means we need the molar mass of H2. So back to the periodic table, 2 hydrogens, each at 1.008, 2.016 grams per mole for hydrogen. We are again going to use that as a conversion factor. 5.889 moles of H2. We want the moles to cancel, so it's going to go on the bottom. We want the grams up on top so that we do end up with grams. They will cancel. We're basically going to multiply. We're going to times this by 2.016. And at this point, we will clean it up to about 4 significant figures based off of the first number, which was right here, which was 4 in this particular case. That number is what it means is if we threw into this reaction 81.75 grams of lithium and everything went perfect, no side reactions, you weren't a clutch and you spilled it all on the floor, you should get out, in theory, 11.87 grams of H2. This is why this is known as the theoretical yield sometimes, which is the maximum amount of product you should produce based on what you start with in the equation. One final thought here for today. We can do stoichiometry, by the way, going from left-hand side to right-hand side to left-hand side. You could do stoichiometry by staying on the left-hand side of the arrow. You could also do stoichiometry by staying on the right-hand side of the arrow. Sometimes people think you always have to kind of go across the arrow for the relationships. You could do it to everybody on the same side. You could do them on opposite sides. You could do this for everybody. You also can do this calculation all in one big calculation and not get the answers in between, or you could get the answers in between. Again, I would not round too much if you do get the answers in between. Again, hopefully you can see a pattern here. Same 4 steps. Just follow those steps. Any questions on that there? All right, we're laid up for today.